Hello and welcome to this section of the chemistry tutor where we're going to continue using these redox reactions to solve stoichiometry problems. So it's big picture a three-part process. First part is we're going to read the problem and interpret it. The second part is we'll write the reaction that problem describes and balance it using the method that we've learned already. And the third part is we'll use that balance reaction to calculate whatever it is that the stoichiometry problem is asking us to calculate. So that's the third part that we've done in the past with easier types of reactions. And so what we have now is a stoichiometry problem that goes like this. In an acidic solution, this is called a permanganate ion. This permanganate ion reacts with tin, this is tin, this tin ion, to give a manganese ion and another tin ion with a different charge. How many milliliters of 0.230 molar potassium permanganate solution are needed to react with 40 milliliters of 0.250 molar tin chloride solution? When you read these problems, they can just make your head spin if you just don't attack it in a logical way. I mean, I've been doing these problems a long time, but even when I read this, and I have the solution right here, even when I read this, my brain doesn't really know off the top of my head exactly how I'm going to get to the answer. I mean, I have the process in my head. I know what I need to do because I've trained myself and I've done enough of these problems. But you cannot read one of these problems and just know, all right, well, this is how it's going to happen. You just can't because there's too many things. There's these different ions going on. There are these different molar solutions, and your brain is like, what are those for? And then, of course, you've got the stoichiometry and everything else. But the big picture is that you need to realize the reaction or the problem is giving you a lot of information. First, it's telling you it's an acidic solution. So that's important. We know that that's now important. We know why. So it's acidic solution. Then it's telling us that this ion reacts with this ion to give this ion and this ion. So it's telling us basically the net ionic equation. It's telling us all the ions that are involved in this reaction. So it's telling us this ion reacts with this one to give us this one and this one. So we'll write that down in a minute. And then the second part of the problem is asking us how many milliliters of a certain solution of this. Notice we have potassium permanganate here. Notice we have tin chloride here, but there's no potassium or tin mentioned in any of the top part of the problem. And I mentioned this before, that confuses a lot of students. What's going on here is you don't buy a permanganate ion in a bottle. You don't go buy a tin 2 ion in a bottle with a charge of +2. You buy established compounds, like potassium permanganate or like tin chloride. Now these are in solution, right? Different concentrations. We've talked about concentrations before. What happens is whenever you perform the reaction, these guys are actually dissociated. So the potassium is an ion and the tin is an ion that are what we call spectator ions. So they don't show up in the full-blown form of the equation because they just hang around and do nothing. The relevant parts of what are happening here is the permanganate ion, the tin ion with a charge of +2, the manganese ion with a charge of +2, and this tin ion with a charge of +4. So let's just jump right in and see if we can make some sense of this. First, we need to write the reaction down, and it tells us that in the problem. So what we're going to have is this permanganate ion, MnO4, has a charge of -1, plus it says it reacts with this tin with a charge of +2, and it says it yields this manganese, which has a charge of +2, with a tin with a charge of 4 plus. So this is the basic reaction. This is the net ionic equation because you can tell for two reasons. Number one, the ions are everywhere, so you know that it's involving the ions. And the second part is the actual stock solutions that contain this permanganate, for instance, is actually potassium permanganate solution. And the stock solution that contains this is really tin chloride solution. But you don't see any potassium or any tin in this equation anywhere. And that's because the tin and the potassium end up being what we call these spectator ions. So when you're writing a net ionic equation, we learned this a long time ago, when you're writing net ionic equations, you don't write the stuff down that doesn't participate. You just write the things down that are actually changing charge or changing amounts or something like that. And so that's what we have left with. That's why the first part of the problem describes that. All right, now that we have that out of the way, this is the net ionic equation. So if we follow our procedure that we've been doing the whole time, step one is always to write it in the form of a net ionic equation, and that's done for us. That's given to us in the problem. And many, many, many times that will already be done for you in the problem. Now step 2 is to write it as half reactions. We've been doing this enough where you can probably remember that. Now this manganese is going to go with this, so what we're going to have is MnO4, charge of -1, going to Mn2+, right? And then the second half reaction is this tin ion with a charge of +2, giving us a tin ion with a charge of +4. So that's all we did, is write it down, write what goes with what. We're not balancing anything yet or anything like this. So step 3 is we do what we call the initial balancing, which, it's kind of shorthand. I've written it down many, many times, but what we've been meaning when we talk about step 3 is balancing everything except for hydrogen and oxygen. So the manganese is balanced with the manganese, the tin is balanced with the tin. The only other thing I have here is the oxygen, so I don't need to mess with him now. Step 3 is complete. All right, that initial balancing is complete. Step 4 is the balancing of the oxygen with water, H2O. We've done that enough times as well. So for the first half reaction, we have MnO4 going to Mn2+. I have 4 oxygens, so to balance that, I need 4 waters so that I can get 4 oxygens here. The second reaction doesn't even contain any oxygen, so I'll just carry along. All right, just like this. So I've balanced the oxygen using water. I have completed that. Let me move over to the other board and we'll work on the next step. So after we balance the oxygen, the next thing we always do is to balance the hydrogen that is available, or that is prevalent, with hydrogen ions. And again, this is acidic solution, just to remind you. So let's go ahead and write that first reaction down again. We have MnO4, like this, going to Mn2+ plus 4H2O. So this is the first half reaction. I need to balance the hydrogen. I have 8 hydrogens over here, so the only way I can do that is to put 8 hydrogen ions over here. Now the second half reaction doesn't contain any hydrogen, so I'll just write it down. 2+ going to 10, 4+. All right, so I have balanced the hydrogen on both sides of the reaction. Now step 6 is to balance the charge with electrons. And what I mean by balance the charge, I mean look at both sides of the reaction and then sum up the charges and figure out where the electrons need to go. So I have 8 hydrogen ions plus MnO4 negative going to Mn2 plus 4H2O. All right, and then on the left-hand side, I need to sum my charges up. So I have positive 8 from here, minus 1 because there's only one of these guys. So this is positive 7 on the left-hand side. That doesn't look like a 7, so I'll do it like this. It's positive 7 on the left-hand side. And on the right-hand side, I have positive 2 from here. The water doesn't count because it's neutral. So I have a positive 7 on the left, and I have a positive 2 on the right. So let me ask you a question. Where do I need to add electrons? I always add it to the more positive side, and I'll need to add 5 electrons here so that I can drag this down to match the right-hand side of positive 2. All right, so we're done with balancing with electrons, so then I'll have the 10 going to the other 10 ion. And this is pretty trivial, but we'll just do it totally explicitly. This has a charge of positive 2, this has a charge of positive 4. So where do my ions need to go? Well, I add them to the more positive side, and I'm going to add 2 electrons. So then I drag this 4 down to be a 2 to match the other side. So I've completed step 6. I have balanced the top reaction by adding 5 electrons, and I've balanced the bottom reaction by adding 2 electrons. But as we've noticed almost every one of these problems we do, what we're doing here is gaining 5 electrons in this half reaction, but losing 2 electrons in this half reaction. So clearly we can't really add them together and recombine them yet. They have to balance. And that's exactly what happens over in step 7. So step 7 is we balance the electron gain loss. And then we add these reactions together. So what we're going to do is, we'll use purple, we have 5 electrons and 2 electrons. These guys are not multiples of one another, so we're not going to be able to just multiply one of these equations. what we need to do is multiply the top guy by 2 and the bottom guy by 5. And if we do that, we multiply this times 2, we'll have 10 electrons. We multiply this times 5, we'll have 10 electrons here. So that's what we're going to do. We're going to start here, and we're going to multiply by 2. So 5 times 2 is 10 electrons. 2 times 8 is 16 hydrogen ions. 2 times this is 2 permanganate ion. On the right-hand side of the arrow, 2 of these manganese ions. And then I have 4 waters, so times 2 is going to give me 8 waters. Okay, so the top reaction is complete. I've just multiplied everything by 2. Now let me go ahead and switch colors down here and say, all right, let me multiply this guy by 5. So I have 5 10 ions going to 5 10 ions with a different charge plus 10 electrons, because 2 times 5 is 10 there. So now I have 2 half reactions that are balanced, and also I have 10 electrons that I'm gaining and 10 electrons that I'm losing, so I'm clear to add these guys, which is the last part of step 7. So I add them. Everything on the left-hand side of the arrow, actually this is all that's over here, so everything here is what I'm going to write down. So I'm adding these together. I'm going to have 10 electrons plus 16 hydrogen ions plus 2 permanganates, O4, charge -1. Then I have 5 10s. And then on the other side of the arrow, I have the 2 from here. Then I have the 8 waters, right? And then I have these guys, the 5 10s. So let me just write it underneath here. 5 SN4 plus 10 electrons. All right, that's everything on the other side. Now step 8 is to cancel. So let's go to step 8, okay? Cancel. That means cancel everything we can. Now we know that we have to cancel electrons. We never want to see electrons in a final reaction. So the 10 electrons cancel with that. Let me look, 16 hydrogen ions. I do not have any hydrogen ions over here. I don't have any permanganate ions over here. I don't have any 10-2 ions over here. I don't have any waters common, so I'm done. So let me just double check my reaction and make sure that it's right. So what I have, 16 hydrogen ions plus 2 permanganates plus 5 10-2 ions goes to 2 manganese ions plus 8 waters plus 5 10-4 ions. So that's correct, at least according to my paper. Let me double check it as far as writing it down and double checking it as far as the balancing itself. So I have 16 hydrogens, and on this time, this side 8 times 2 is 16 hydrogens. I have 2 manganese. I have 2 manganese. I have 2 times 4 is 8 oxygens. So I have 8 oxygens over there. I have 5 10s. I have 5 10s. So as far as elements, as far as mass and moles and all that stuff of elements on the left and on the right-hand side, I'm done with that. Now let's look at the charge. And so for the charge, just to make it totally clear, I'm going to write the charge down here. I have 16, positive 16. This is -2 because 2 times 1, so I have -2. And then this is 5 times 2, so this is positive 10. So what I'm going to have here, 16 minus 2 is 14 plus 10 is 24, positive 24. And on this side, what I'm going to have is 2 times 2 is positive 4. The water counts as nothing, and then 5 times 4 is 20. And of course, this becomes 24. So 24 and 24. So I've shown myself, proven to myself, that the elements balance on the left and on the right-hand side, and the charges, whatever the sum of the charges are, they balance on the left and on the right-hand side. So this equation's balanced, okay, and this is done. So what I'm going to do then is rewrite this equation, because we really need to work on the stoichiometry at some point here, right? So what I'm going to do first is I'm going to rewrite the final reaction, the balanced reaction, here. So this is 16 hydrogen ions plus 2 MnO4 negatives plus 5 SN2 plus yields 2 Mn2 plus plus 8 H2O plus 5 SN4 plus. So this reaction is exactly what we just had from before. I didn't change anything. 16 hydrogens, 2 permanganates, 5 10s. 16 hydrogens, 2 permanganates, 5 10s. On the right-hand side, 2 manganese, 8 waters, and 5 10s. So 2 manganese, 8 waters, and 5 tens. So the reaction is the same. Now let's read our problem again and see what we need to do. So we've done the first part. Now it says how many milliliters of whatever this concentration is, potassium permanganate solution are needed to react with 40 milliliters of this concentration tin chloride. So what I really want you to keep in your brain is it's giving you some information about potassium permanganate and tin chloride. Potassium permanganate and tin chloride. Okay, on the left-hand side here, I have permanganate here, and I have tin. So what's really going on here, all right, what's really going on here is, when you think about it, this guy is really 2 moles of potassium permanganate reacting with the ratio of this guy, which is 5 moles of SnCl2. Make sure you understand that. All I'm trying to say is that, look, you don't buy from a bottle permanganate ion and dump it into a solution. You don't buy tin ions and dump it into a solution. They have to come from somewhere. The problem is telling you where they're coming from. It's just not being so explicit. It's not saying, hey, you put these things in solution and it breaks down and this is where your ions come from. It's kind of assuming that you know that a little obscurely. That's what's going on. It's telling you that this stuff, this potassium permanganate, is reacting with this tin chloride. Because your reaction doesn't involve potassium or this chlorine, because it doesn't involve the potassium or the chlorine, then you just need to know that those are spectator ions and they're not really participating any. They're just kind of hanging out there. So the relevant parts of it are the permanganate and the tin, which is all what's given here. And so the reaction that we have at the end of the day, the reaction that we have is telling us, this net ionic equation that we've balanced here is telling us that 2 moles of permanganate ion react with 5 moles of tin ions, tin with ion charge of plus 2, right? Tin 2 ions is what we call it. So the ratio is 2 to 5. So if the ratio of this ion is 2 to every 5 moles of this, 2 moles of this for every 5 moles of this, then it stands to reason that 2 moles of my real reactant must be reacting with 5 moles of this reactant. And that's what we're really trying to show here. We need to know the molar ratio of whatever it is that we're talking about in our problem, which is spelled out for us, which is this potassium permanganate and this tin chloride. And we get it from the reaction. So that's where you're probably pulling that information from. Now, to confuse it a little bit more, we're not just dealing with moles, we're dealing with molar solutions, right? So what I want to do is set that up. Notice what we start with. We start with 40 milliliters of this concentration of this. All right, 40 milliliters of that. So let's work on that. All right, notice we don't have grams anywhere. There's no grams in that problem, so we don't need to find the molar mass, grams per mole, like we do in some problems, because we're just dealing with moles and with milliliters. So let's go down and see if we can figure out how to write this down. We want to start with what we know. And what we know is that we're starting with 40 milliliters of SnCl2 solution. That's what we're starting with, because that's basically told to us in the problem. We're trying to figure out how many milliliters of that solution do we need of this stuff. So we have to march through with the unit conversions to pull that off. First of all, this is 40 milliliters. And when you're dealing with molar concentrations, it's moles per liter. So you can't deal with milliliters. You have to convert to liters. So the way you're going to do that is 1,000 milliliters of SnCl2 solution is equal to 1 liter of SnCl2 solution. All right, so the only reason we put this step in here is because this milliliter here is going to cancel with this milliliter. And so now with this conversion done, if we stop here, now we know how many liters of this solution we have. All right, now if we go back to our problem for the tin chloride, okay, we're told how many milliliters we have. We're also told the molar concentration. That's how many moles per liter. How many moles per liter. Now I'm going to switch colors here to make it a little more readable. We'll have to continue on the line underneath it, pretend that this is right here, all right? So now we know how many liters that we have here. Now we know from the tin chloride that for 1 liter of SnCl2 solution, it's 0.250 moles of tin chloride. That's what moles per liter is. When you have a molar concentration, it's that many moles per liter. So here I know I have 0.25 moles of this stuff for every liter of this solution. That's what the molar concentration is given to us in that problem. Now, if I stopped here and just did the calculation, then what I've calculated is how many moles of tin chloride I actually begin with, because I'm told I have 40 milliliters. I do all of this stuff, and now I know that in those 40 milliliters I start with, I actually have calculated how many moles of tin chloride, the actual substance, I actually have. And once I'm at this step, now I use my molar ratio, because now I know that 5 moles of tin chloride reacts with every 2 moles of potassium permanganate, right? So that ratio is locked in. That comes directly from the chemical reaction, and we would not have been able to do that without balancing that reaction. All right? So if I stop the calculation here, I know what I've started with, and I've calculated how many moles of potassium permanganate are required to react with that, right? But I can't stop there because I'm asked how many milliliters of that solution. So when I go back and look, I'm reacting with potassium permanganate solution. The molar concentration is 0.230 moles per liter. So the way I'm going to write this is I'm going to say 0.230 moles of potassium permanganate. Moles of this guy reacts with 1 liter of potassium. I mean, it doesn't react with, it contains potassium MnO4 solution. So if I've done my unit cancellations right, I've got moles of potassium permanganate canceling with moles of potassium permanganate. Now I've got it into liters of that solution, but it's not asking me how many liters, it's asking me how many milliliters. So I gotta go ahead and convert that final answer to milliliters. So what I'm going to have, right, is I'm going to have 1 liter of potassium MnO4 solution is 1,000 milliliters of potassium MnO4 solution. This is a great example of when I say that this unit conversion, dimensional analysis stuff, is really one of the most powerful things you can learn in all of science, because it helps you out so much. So let's do this math here and figure it out. So in your calculator, you put 40 in there, then you multiply by 1, then you divide by 1,000, then you multiply by 0.25 and you divide by 1, then you multiply by 2 and divide by 5, then you multiply by 1 and divide by 0.230, then you multiply by 1,000 and you divide by 1. And when you do all that math strung together, what you're going to get is 17.4. 17.4 what? 17.4, the only unit left is milliliters of KMnO4, potassium permanganate solution. And that's the final answer. 17.4 milliliters of that solution is needed. You know, when you look at the math on the board, it's just multiplication and division. The math isn't hard, it's figuring out how to set it up. So what we did is we started with this reaction, which was really given to us in words. We wrote it down and we balanced it. And when we finally did all the method of balancing that we've learned so far, we ended up with this reaction at the top of the board up here, which tells us that for every 2 moles of this permanganate ion, it reacts with 5 moles of this tin ion. But those ions are coming from somewhere, so it tells us that really 2 moles of potassium permanganate is reacting with every 5 moles of this tin chloride. So that's the molar ratio we care about, because in our original problem, that's what we're really told is reacting there. That's the solutions is what we have. So we start with 40 milliliters of this tin chloride solution. We convert it to liters. And then once we have it in liters, we use the molar concentration in moles of this per 1 liter of this to basically find how many moles of tin chloride we start with. Then we use the molar ratio that we found from the reaction to find out how many moles of this potassium permanganate would be required, and then we use the molar concentration to go back to liters, and then we use the unit conversion of liters and milliliters to get down to milliliters of solution. So it's like in the core of this, you know, present or birthday cake or whatever you want to call it, the core of it is really in the middle what we found from this reaction, the 2-to-5 ratio. That's really the most critical part. That's the piece that you really needed in order to solve the problem. It just took a long time to get that piece, the ratio of 2 to 5. Everything around it is like a little Christmas tree hanging off of it. You start with milliliters, you go to liters, you go to moles. Okay, now you use the reaction to jump from one reactant to the other. Okay, that's locking that in. And then you go back to liters, and then you go to milliliters. So when you have these reactions that deal with molar concentrations, try not to think of it in terms of molar. I know that that's what we learn in the books, but try to think of it as, all right, this is not 0.230 molar, it's 0.230 moles per liter. It's a conversion factor telling you how many moles in every liter. So just think of it in terms of that, and then you can arrange your units to cancel as needed. So if this kind of thing confuses you, you probably should go back into my previous lessons, many lessons ago, and look at our reaction stoichiometry that deals with solutions. I've done a lot of problems like this before. What we've done here at the end is really something we've actually done before, but we've just used the net ionic equation to get the molar ratio. That's the new part. So make sure you know how to do this problem. I guess if I had to sum up one thing that I would say is that the stoichiometry skills that you learned earlier in chemistry are very important. These things that we're doing here are not really hard. The only difference is we have to go through all this mess to balance the reaction before we can even do anything. The rest of that logic, once you get to that point, is stuff that we've done before. So make sure you understand this problem. Pause the video, grab a piece of paper, write this down, see if you can solve it yourself. Even if you've just seen it just now, and 5 seconds later you're trying to work it yourself, you need to prove to yourself that you can carry yourself through the logic. I promise you that seeing it now is not going to change that. So go and do that yourself, prove to yourself that you can do it, and then follow me on to the next lesson where we will continue our challenging lessons in chemistry and mastering these concepts.